Hello everyone. This is Samarth, Data Science and Artificial Intelligence second year at IIT Roorkee, and I'm here to discuss on the applications of single value decomposition for the next couple of minutes. So this will be our flow. We'll start off with SVD, talking on PCA, before moving on to some applications of image processing, computer vision, natural language processing, and medicine. And we'll end up with a case study, a practical approach. So before diving deep into the applications of SVD, let's first discuss what SVD actually is. So SVD is a technique to decompose a matrix into three component matrices to obtain essential information regarding it. The formula to decompose the matrix is A equal to U sigma V transpose, where U is a left and right singular matrix respectively, which is while the sigma is diagonal singular value matrix. So basically, it's a we can see the simpler representation of the components here. We should also note that the dimensions of U, sigma, and V transpose matrices. So like you can see here, it remains conserved when they are multiplied together, which is the main important issue. So in order to understand the meaning of the three components, let's first have a look into an example. Let's suppose we have an image. The V transpose matrix first rotates it, then the sigma matrix stretches it, and finally the U matrix rotates it with a slider tilt. So here's a visual representation of the same. Here we can observe that there is a 3D object which is turned into 2D without losing any data. We can notice it first rotates its direction using V transpose matrix, then it stretches using a singular values, that is sigma matrix, and finally it gets tilted. So it's somewhat a basic application on how things work out in SVD. So now let's move on to properties of SVD, which is widely used in matrix approximation and its application in data compression, noise reduction, etc. Both U and V transpose matrices are orthogonal. Also, we may also remember that we are restricted. You may remember that we are restricted to only square matrices for finding inverse, but in SVD, it's got you covered. It allows you to easily find the pseudo inverse of the matrices using the formula given below. So now SVD finds its way to one of the important mathematical applications in the world called PCA, which transforms the data into principal components for better calculations. SVD is used to find out U and sigma, which is used to for the calculations in PCA further. So now let's move on to some industry applications of SVD. First, we'll talk about image processing using SVD. So let's first dive deeper into it. We all know that images are composed of matrices of high dimensions. So SVD simply decomposes the image and retains only top singular values, thus reducing the size of U, V, and sigma. It's also noteworthy that compression ratio also can be calculated by the number of singular values in the sigma matrix. So here's a representation of the process. We can notice how the image is broken down into its components and the dimensions are reduced, which then gets reconstructed and multiplied back to the compressed image. We'll discuss more on this in detail in the end if you didn't get it right here. So another noteworthy application is the image denoising, which is used to trim down high frequency details in image into less significant values by using SVD. It's a similar process for the same something similar to what we use in the image compression previously. Similarly, we have image reconstruction, which is used to store degraded images. The process here that it is the first decomposed to matrices, then truncated before final reconstruction. Let's move into computer vision using SVD. We'll first take up facial recognition. So it's something we use in everyday world, where the lock has become a pretty common thing. It is used as a technique called eigenfaces, which constructs the image in different angles and then validates it. Another one is object detection, which is actually used to detect object in video frames and can be found out in wider use these days. Okay, so now let's talk about NLP. So natural language processing or NLP, SVD finds its way in latent semantic analysis. So now what's LSA? Let's find out. So it's actually a technique to find out a pattern and draw relationships in text documents. So here's a matrix representation is that the U matrix represents the term relationship and the V transpose represents the document relationships. It then draws semantic relationships, which then simply finds the relationships between the text, and LSA helps to identify hidden themes in the related document. So here are some benefits and the future directions of it. Okay, so finally, SVD finds its way in different fields of medicine such as MRI and CT, where it is avidly used in tumor cancer detection, etc. So now let's move on to practical functioning of image compression of SVD to make things clear.
So we'll first of all import NumPy library, which I'll be using for mathematical calculations, and the PIL library, from which I'll be using the image module for handling of the image that I'll be using for image. Now I'll first define a function called openImage, which will open the image using that image.open, and then it will split it into three channels, red, blue, and green, for better purposes. So now next we have a function which compresses it channel by channel. So I'll be running it three times, red for red, blue, and green, which is tasked to reduce the matrix to k singular values, which I'll be specifying later in the program. So let's first see the original image, which is this. Okay, so now let's see the parameters that I've set. I've set image width and image height to be 512 to be standard, and I've set the singular values limit to be 160 at this moment. So let's so after it first compresses all the three channels and then converts them into different images, red, blue, and green, and then merges it. This is how the program is working. So let's see how it looks after the process. So my data shows that the image that will be produced is 62% of the original image, that is 62% around compression is there, and if you compare it alongside we can clearly see there's a bit of a reduction in the quality, but it's not that much visible. Now let's reduce the singular values limit a bit. It's actually what happens is that the singular value limit is the is singular values. So now I'm reducing it to 100. So let's see. So here I can see it's about 39% of the original image. Let's open the original image as well. So if you can see, you can cite the differences here itself. The left ones is the compressed image and the right one is the original one. You can see the quality is getting degraded a bit. If I reduce it further to 50, you can clearly see that the edges get blurred and there's no sharp edges that I can see. Okay, so let's increase it a bit. If I increase it to 200, for example, you can see the quality gets increased. So this is what the image compression means and how SVD can be applied to it. Thank you.
So in the end, I would like to conclude that SVD spans diverse fields and can be viewed as a cornerstone in most of the technical applications. So thank you for bearing with me this while and hope you all liked the video.